COVID has affected the automotive industry worldwide, but it has least affected the EV segment. Electric vehicles have caught the fancy of automakers and policymakers alike in India and around the world. With the government's push to make India a 100% electric vehicle nation by 2030, automotive companies are carefully treading into the EV space to expand their portfolio. Our next session is on Reimagine EV Development with Virtualization. I would like to welcome Mr. Sheetal Kumar Joshi to talk about virtualization in EV verification, component and system verification, and battery verification. Welcome, Mr. Joshi. Over to you.
Yeah, before I start, it's customary to introduce my company. ANSYS, we are into engineering simulations, founded 4 decades back as a mechanical company, but over the years we acquired about 27 companies and about 50 technology partnerships. So we added physics like mechanical, electrical, fluid dynamics, thermal, as well as optical, and the embedded software. The latest acquisitions being, which I want to call out, is AGI and Phoenix Integration, which puts ANSYS in the domain of MBSE as well as systems of systems. Okay, with that introduction, let me jump to topic of electrification. EV has complex play of multiple physics, mechanical, electrical, thermal, electrochemical fluids, and magnetic. On top of that, this physical device are governed by the softwares, control softwares. Designers need to make sure of functional safety, and that makes system engineering highly complex subject. Now, we have seen many cases in industry while tuning the control software alone, the range of EV has increased by 20 to 40%. Same hardware, nothing changed, but changing the controls changed the range. So what it means is a complex play of physical design and software is necessary. Okay, and that's one of the trends that I'm going to discuss in the next slide. And what organizations are doing are integrating software and physical design at quite early stage. This is a EV validation and testing diagram. You could consider it as a right side of the V. Okay, so typically we start with a component system where you have physical design of motor and battery, as well as simultaneously software team works on the controls like BMS or motor control and so on. Okay. Similarly, next stage would be a subsystem or powertrain system analysis where all components are integrated, as well as vehicle control softwares are also developed. Now over here, there are certain tests that are necessary to be done for regulatory as well as final quality checks that are physical tests are done. But what organizations are now doing globally is, and what you see is this green components, are combining the physical design and controls in a virtual validation environment. And what it requires is high fidelity physics-based model. That's kind of a key. This is the key behind this entire approach that starts with component and goes to the powertrain system. Now, if you have developed a good virtual approach for component and powertrain system, it can be easily extended to the vehicle level simulation. Now, this has a tremendous advantage. What it enables is getting this entire tests that you need to do in the different terrain and different scenarios, those can be virtualized now. So that was the first trend of integration of software and hardware. Let me go towards the second trend, that is combining of physics, data, and simulations. Okay, so we are in era of new product development as well as new technology development. Both are happening simultaneously. Okay, so getting the reliable plant model for validation is very challenging. And we already saw that integration of physical design and software is one trend. So here, what organizations are doing globally is creating modular physics-guided learning framework, which integrates physics as well as data, physics as well as whatever test data that you get or low fidelity model data that you get. This can considerably improve the accuracy of data-driven predictive engines. And the chief idea of this approach is augment the knowledge of the simplified theories or models with underlying learning process. And that considerably reduce the product development time for getting the accurate plant model. And I'm going to show one example in the next section. Okay, so we saw trends in virtualization. Let me show you how it applies to powertrain component validation. And I'll continue the machine learning discussions that we had, how machine learning is actually helping the creation of the plant model. So this method we call is a fusion model, where there is a cheap function or less expensive function with an analytical model, which can be done quite fast, maybe kind of it can run within kind of a few hours. You can get several data points, and a costly function where you need to do full 3D physics simulations or even carry out a test. I have given example of the 3D physics, but you can consider it as a test as well. If you combine these two, you can get the same accuracy of the costly function. But advantage over here is you have to do much lesser costly functions analysis. What it means is, if you are doing a 3D physics-based simulation, if you need about 400 to 500 data points for a motor for characterization, with this method, you can get away with 400 or 500. Instead of that, you can get over with 40 to 50 data points only. Similarly, the same things apply to test also. On test bench of the motor, it can take about 6 weeks or so. But applying this machine learning based techniques, you could reduce to 1 or 2 weeks for the motor characterization. So that's the power of combining physics as well as data science. Okay, so let me go to another example of the motor, where we'll look at the motor control as well as physical design, how we can integrate together. Now, based on accuracy of plant model, we often see the differences between what you had originally thought of and what you find from test, the difference in overshoot and response delay, and that results in recalibration of the entire model. So what you can do to resolve this problem is get a very high fidelity model simulated through 3D physics. And good part is nowadays 3D physics solver for motor can predict about 95% accurate as what you would predict from the bench test. So if you can get as accurate model as bench test, you could probably process that raw data through MATLAB or any other scripts and create what we call is reduced order model. Now, this reduced order model is a very powerful concept. FEA 3D simulations can take you days, so you cannot integrate with control, but reduced order model generated from FEA, that runs in seconds. So you can now control, you can add it with the control, and now you have hardware as well as software. Both are accurate definitions in a single simulation environment. And once you get those definitions, you can carry out, all sort of the control tunings, as you can see over here. That kind of high fidelity or test data or 3D physics would match quite closely with the reduced order models. So that's the more detail about how motor control implementations can happen, where the concept, the trend that which I mentioned, taking the software and physical design together to carry out the validation. Now, this methodology is already being applied, okay, and it is practiced across the OEMs across the world. This one is a Porsche Formula E team example. The team had goal to become, champion in the last year season. In order to achieve this, team needed to design, integrate electric drivetrain with a consideration of every drop of energy that can be saved. And this requires optimization at the system level, subsystem level, considering the component interactions and dependency. Okay. So over here, Porsche is front loading the simulations towards the left of the V cycles, verification of software and hardware. They characterize the traction motor exactly the way which I mentioned in the last slide through the 3D simulation environment. And that model is imported in what we call is twin builder, a reduced order model, and rest of the system model is modeled to create full drivetrain representation that enables Porsche to run several minutes of drivetrain in a virtual environment. Okay, so that's the kind of a example of the philosophy or trend that I mentioned about how software and physical design can be combined together. This is not limited only towards the motor, but same can be done with the battery also. I'm not going to go in more detail, but just very briefly, you could create your electrochemical model and thermal model combined into battery and get a very powerful, very accurate, very fast executing reduced order model, and which then can be combined with the BMS. Okay, so far you have seen two major trends which I mentioned: software and physical design, as well as machine learning, and how these trends can be applied to powertrain component validation. So we'll see how this entire methodology that we discussed earlier fits into the virtual test, complete virtual test. And over here, what we are doing is we are integrating the physics model derived for powertrain, that is the battery and motor, in earlier section, as well as power electronics as well, and combine that with the other vehicle models like clutch, transmission, wheel, HVAC, and all. This all can be combined even with the virtual environment of your drivetrain and scenario. If you are driving in kind of a hilly region, or you are driving in desert, or you are driving in a very cold region, pretty much everything can be, all parameters can be studied. And what this helps is, now that you have very accurate powertrain models that we kind of discussed in the previous sections, you already have the vehicle models. So whatever drivetrain that you will be carrying out, that will be highly accurate. And it's not just kind of you get a macro parameters for the drivetrain of range and all, but you can pretty much measure the cell temperature, each cell temperature ranges of the vehicle, current, performance, motor torque with the drivetrain scenario. Okay, so, and once you kind of create these virtual systems, it takes time to create this, but once it's ready, you could carry out like hundreds of validation scenarios in this virtual system. So one of the examples that I'm showing over here is how this virtual platform, once it's get ready, can help you to carry out various scenarios which practically may take long time and expensive. And this over here, it shows over here that battery electrothermal, very highly accurate model that we already saw, motor models, software FMU, all are combined. In fact, if you do not have some of the models that happens in today's scenarios, where some of the models are coming from vendor, you could also put calibrated test data in the system models. And then we can carry out the range prediction. This one is showing three different scenarios. Let me just take a click back and come. Three different scenarios where we have freeway exit, or urban scenario, or traffic with signals starting and stopping vehicle, how the range of electric vehicle get changed, and that can be predicted pretty much in the virtual environment. So this approach can be also extended to hardware in loop or embedded software modeling. And we are not going to detail into this slide, but the key message is whatever methodology we developed earlier, especially the high fidelity plant model, that can be combined with the software in the core simulations in a model in loop. Those plant models are also consumable in the hardware in loop. So what it means is, even if you do not have your motor or battery physical prototype ready, if you have a detailed design available, you could create a reduced order model and place into consume it into your hardware in loop. So before even getting your motor physical prototype ready, you could carry out the validation test for that motor. So this provides a very, very powerful approach. And just to summarize, once such virtual platforms get created, you could do hundreds of drive validations with vehicle parameters, requirement, constraints, all in combinations. You can do a design of experiments. It's a virtual test, virtual integration, virtual validation approach. And finally, this virtualization helps in not only the validation, but also software calibration, and probably extending more. We didn't talk today, but prognostication of health of the vehicle. So I hope that provides you a good idea about the trends in the product development that are going on, as well as some real life example of how component and system level validations are being done. I'll be happy to have answered any questions, you can reach out to me on the contacts mentioned over here. Thank you very much for your time.
Thank you, Mr. Joshi, for an informative session on EV development and virtualization. Now let's move further and explore more.